they're actually lower results. 60. But hasn't been pushed out. There aren't mixed correlates.
Yeah, I'm ready.
All right, well, let's get going for our penultimate session. So we're very glad to have Sebastian finishing up about the gravitational S matrix.
Right. Well, thank you so much. So before we start with today's lecture, let's review what we've done over the last 3 lectures. So we consider this case of the gravitational S matrix through the lens of the the exclusive scattering of 2 particles. And then we explored these high energy regimes, and we've seen that the exact physics depends exactly on how you approach the high energy regime, depending on how you tune S, and B, the central mass energy, and the impact parameter. Okay, so then we started from the weak coupling expansion. So roughly this plot should be read as going from here to here is the weak to strong coupling expansion, or equivalently elastic to inelastic. Okay, and then we've seen that at tree level we have 1 diagram. Then we've seen the magic of the iconal exponentiation, in which case this diagram exponentiated. This was the leading iconal. And then in the last lecture, yesterday, or 2 days ago rather, we've studied corrections to the iconal phase, which included these so-called post-Minkowski corrections. And then we've seen that there's new effects every time you include a new correction. So here we had some tidal effects, and then the gravitational waves switched in, and things like that. In the limit, as we include all the post-Minkowski corrections, there's supposed to be a resummation, where on the physical grounds we expect to see black hole production to be consistent with the numerical GR computations. And there we expect that the amplitude is exponentially suppressed entropically with the entropy of the black hole, possibly, well, up to F phases. OK, and let me review some of the length scales that we've introduced last time. So we have the Compton wavelength, which is the one in here. We have the Schwarzschild radius, which is this length scale of the gravitational fluctuations induced by the system, and the impact parameter. Okay, so in addition to that, we can also the large separation of scales between this quantity and these 2 gave us the distinction between quantum scattering and classical, which is quantum is roughly in this direction, and classical is roughly in this direction. Okay. So what we're going to do today is introduce a new length scale. Let me call it L. And in fact, this will be the length scale associated with the size, the intrinsic size of the object. So we're going to go beyond the point particle approximation. And more specifically, what I wanted to study today is what happens when we replace particles with strings. So that length scale will be L string, which is the size of the string. Okay. So now we would have to put the size of the string somewhere within this chart. We're going to insist again that it's above the quantum limit, but now we can have different physics depending on how Ls is compared with the radius and the impact parameter. Okay. So at least schematically, we can put it on this plot in here. So let's say we're going to have some transition when B is larger or smaller compared to Ls. And likewise, we can also compare Ls to the Schwarzschild radius, which translates to comparing S with the length scale of the string. Okay, so we're going to have something like twice D minus 3, and then log Ls, just setting G equals to 1 for the purpose of this plot, which is going to be another cutoff somewhere here. Okay, so what we expect to see is that somewhere in this range, there's going to be new physics. And that new physics, in this case, will be stringy. Okay, so this is going to complete more or less what I wanted to get across in these lectures. And we're going to study two aspects of it. So of course, by the universality that I mentioned in the previous case, it has to be that this transition here is somehow smooth. So we will have to see how from the stringy computation we recover these limits. And this is what we're going to do today. In the first part of this lecture, we're going to recover the iconal in this direction. So this is a rigorously established result. But I think the story would be less fun if we didn't include any speculations. So what I wanted to tell you more about in the second part of this lecture is some speculation of how we transition between the stringy regime and the black hole regime. All right, so that's the plan. Is there any question about the, yes? The question is whether in the low energy regime it's equivalent to finite size effects. Yes, so there's two sources of finite size effects. One was somewhere here, which was these tidal effects. So you can include that. This will be visible even beyond the string scale. But there will be additional finite size effects that have to do with the intrinsic size of the string and all the excitations that run through the string.
But if LS is just the size of my object, whether or not it's a string,
Yeah.
then I would expect the tidal effects to scale with the size of the object.
Yeah, exactly. So we're going to take the question was what if it wasn't a string, but it was some other object with the same scale. Similar type of physics would happen, although it's less explored. So I will stick with this model to be concrete. Okay, so let's start with the stringy corrections. Okay, so the rough idea is that I want to replace this diagram at tree level with some kind of stringy diagram. So what I will consider is scattering of closed strings, which is usually computed using worldsheet methods. So this scale LS is roughly this size. And then for completeness, let me also mention that it's very usual in the literature to call it square root of alpha prime s, or identify these two scales. So this is the string length. Okay, so just like we've done the computation for this diagram, now we have to do the computation for this diagram. So this is a famous scattering amplitude called the Mizera-Shapiro amplitude. So how many of you have seen the Mizera-Shapiro amplitude in the past? Okay. Oh, wow. Okay, almost everyone. But there's a question as well.
So yeah, why are you assuming the critical string here? Because the way you were saying it, it seemed like a very generic string, right? You just introduced some new length, but
Yeah.
this is clearly like a very special string.
Yeah, so the question is, I think, what is the string state and whether it's generic or not? Is that the question?
Why are you assuming the critical string as opposed to a non-critical string?
Oh, why it's critical? Yeah, just because most of the computations have been done in the setup, so I'll review the critical string. So more specifically, what we're going to do today is the type 2 superstring, which is defined in 10 dimensions, although at tree level, you can use the same formula regardless of the dimension. And what we're also going to do, which is to do with the typicality of the external states, is that we're going to put massless external states. Massless scalars, rather. And that's just to match on the GR computation. Okay, so let me write the formula. It's actually, maybe I should move on to this blackboard. So this is going to be tree-level scattering in string theory. as a function of s and t. Okay, and then the formula is as follows. So all of you have seen it in one way or another, apparently. So let me just write it down. One thing that we're going to see straight away is that it's going to be manifestly both symmetric or crossing symmetric, which means it's invariant under the exchange of s, t, and u. There's some rational factors, and there's also these gamma functions. Okay, it's a wonderful formula. You can read off a lot of physics from it. For example, you can read off the positions of the resonances, which are given by these gamma functions in here, which tell you about the spectrum of superstring. Let me also mention here, by momentum activation, you've seen this before, s plus t plus u is equal to 0, so I can always eliminate u in terms of s and t. And the last comment here is that I've identified, usually there would be a string coupling here, which would be called, in this case, G string squared. But to identify it with our GR from before, we identify the string coupling GS up to some numbers with G Newton divided by mass dimensions, the string scale to the d minus 2. Okay. So first of all, let's convince ourselves that this formula is a deformation of the gravitation of, well, basically that this picture is valid. Okay. So what we can do is we can take the Born limit or alpha prime goes to 0 limit. This is the limit in which alpha prime t is much, much smaller than alpha prime s, which is much, much smaller than 1. Okay, and then here the idea is, well, you can just look at this formula. The only thing they need to know about the gamma functions for this purpose is that gamma of 1 is 1. Okay, in this limit, the 1 dominates over all the alpha prime factors. So all of these gamma functions disappear. And moreover, because of this limit here, t is much smaller than s. This term here dominates. And then u turns into minus s. So you have minus s squared over t in the numerator. So indeed, in this limit, the string formula reduces to the QFT formula that we've seen before. Okay, so that was easy. Now let's do the other limit, which is going to be more useful for us. It's often called the Reggie limit. Oh my God. In this limit, we're going to take the s in the units of alpha prime to be very, very large. And we're not going to touch t. Okay, here you need to know, let's see, there's some rational prefactors which are very easy to take the limit on. The most tricky thing is to take the limit on the gamma functions. So here you should, if you do this exercise, you should use the following identity. If you have a ratio of gamma functions, you take the x to be very large, but they're offset by different, by a and b. Then in the large limit, this behaves like x to the a minus b. Okay, so the way that you use this formula is that there's going to be a cancellation between this term and this term. That's because this term can be written as this minus u, which you can write as s plus t. So there's going to be an offset here, and there's going to be a similar offset in here. Okay, so I believe most of you have seen these kind of games before, so let me just give you the final answer.
Do we assume S is bigger than T, or do we not say anything?
No, we don't say anything about how T, for now, we could do that additional limit, but we don't commit to anything yet. Okay, so in this limit, we get the following. This just comes from the prefactors. There's the gamma functions of T, which just come for the ride. So we have this ratio. Okay, from these kind of games, the variable that is large is alpha prime s. Okay, so it's clear that we're going to have alpha prime s to some power, which is to do with these offsets. These offsets are essentially by an alpha prime t. There's two of them, so we get twice alpha prime t. But actually, you have to be a little bit more careful because one of them goes in one of them x is positive, and in the other one x is negative. So that means that there should be a minus sign in one of the factors. So that gives you a phase. So e to the minus I alpha prime t. Okay, and strictly speaking, in this computation, we actually, to determine whether the phase is plus or minus, and to commit whether you're in the upper half plane or in the lower half plane. So this is the result for the upper half plane, which is the physical branch. Yes?
Oliver asked if this was S much bigger than T, and it seems like this is necessary. Like you fix T to whatever, and then take S much larger.
Yes. The question was whether, well, it was a similar question. Whether T is fixed to, whether T is somehow related to this limit, and T is just fixed, or alpha prime T is fixed. Okay? All right. Any other questions? Yes?
Usually, when we go, the strings usually have other states also apart from the graviton.
Yes?
But somehow we are getting answers that are matching purely the
Yes?
GR. Is there like a G string to G mapping that is the only source, or is there some?
So the question is that usually, well, which is correct in this channel, for example, which is the relevant channel here, there's going to be a lot of states beyond just the graviton. We can actually see this. So this is the graviton pole, or that is the massless pole. Is really the whole supermultiplet being exchanged. But okay, and there's also poles associated with these gamma functions. To actually understand the structure of why this is kind of a generic feature, there's a whole theory called the Reggie theory, which allows you to understand why in such limits you're dominated by the highest exchanged particle, which is massless, which in our case is the graviton. Yeah?
Is there any interpretation of the branch pattern as generated?
Yes, excellent. So the question is about the interpretation of the branch cut in S that is being generated. So let me draw a little picture in the complex S plane. If you look at the original formula, you have an infinite number of, let me do alpha prime S plane. You have an infinite number of poles in the complex plane in integer separations. Now what we're doing is we're taking the limit as S becomes very large. So in that limit, you should think of those poles as related to a branch cut, and that's the branch cut that you can see here. So that's the reason why we have the imaginary part in here. Excellent. Okay, so just a little bit of piece of notation. This quantity here is going to appear over and over again. So let me introduce the notation, which is going to be exponential of t, a new variable y, divided by 4, where this y is defined, well, it's just defined to match this formula, which is going to be 4 alpha prime twice log alpha prime s minus I pi. Okay. And then in this y is important because it's going to measure the effective string size. So it turns out that the naive estimate, just like in quantum mechanics, when you send a wave packet, there's the wave packet spreading as you scatter it at higher energies. There's going to be a very similar effect in which the strings have a spreading effect. And this quantity here is going to, the reason why I introduced a new name for it is that it's going to measure the string size squared. So I'm introducing a new variable, which is going to play the role of the effective string size. Ah, okay, great. Should I write it again? Let me just. Let me just keep it here. Let me just keep it here, it's fine. Okay. Maybe I should comment here, just so that it's somewhere here. This is going to play the role of the effective string size. And it might not be clear yet why that's the case, but we're going to see that in the next 10 minutes. Okay, so now what we've done is we've computed basically the analog of the Born pole, the analog of the of kind of this region in the plot. So now one thing that you can do is you can take this answer, you can exponentiate it, and compute the phase shift. So the phase shift is going to be basically the Fourier transform of that object. So let me actually leave it as an exercise. It's doable. You have to use a bunch of identities. But I think we don't have time for that today. Oh, sorry, phase shift, I guess we called it the iconal phase in the previous lectures. Okay, so there's going to be some delta string, which is going to be dependent on S and B. It's a Fourier transform of that object over there. Okay, so there's some prefactors, which is GS divided by B to the D minus 4. This is the same as in the GR case. And there's some numbers, positive numbers here. Okay, and there's going to be actually two terms. The first term is going to be the gamma function of the IR divergence that we've seen in the very first lecture. So this piece is simply the GR term, but there's going to be stringy corrections to it. So the stringy corrections are given by this term. Where this object here, gamma with two arguments, is called the incomplete gamma function. This is the reason why I skipped the derivation, because you need to know some like little special functions for this purpose. Okay. So just to let you know, incomplete gamma function as a function of the arguments, this function here looks typically something like this. It starts at some finite value, and then it decays exponentially with the b squared over y. Okay. So the idea is that this is the GR term, and this is the stringy correction. Okay, this is actually not the complete answer yet. You can tell because there's a lot of space. And this is because this has to do with the previous question of how we scale t with the other parameters. So one thing that I could have done is scaled alpha prime t to be very small. Then these gamma functions will disappear. But it actually doesn't cost anything to include them. And if you're careful about your Fourier transforms, would translate, let me write it as an operator statement, as a derivative with respect to b squared. We actually won't need this factor for anything. It's going to be always 1 in our case. I'm just writing it for completeness. OK. So I mentioned that we have the G. Oh, there's a question?
I just want to understand the b to 0 limit. I guess you would
Yes.
say that
You wanted to understand b to 0 limit, so let's. I'm going to discuss it now. So let me postpone your question. In fact, what I wanted to do first is expand it in the opposite limit. So I'm going to do this limit first. Here, actually, there's a square. Okay. So in this limit, the string iconal phase is going to be equal to the GR phase. So let me just call it delta GR. This is the object that we've studied in the previous lectures. I guess I called it delta naught or delta 0. And there's going to be the correction. And the correction, as you might anticipate from what I said here, that this function here decays exponentially fast when the argument is large. Well, it's going to decay exponentially fast. So we have GS, this. And then exponential. It turns out to be an exponential decay with some power law correction that depends on this argument in here. Okay, so there's the exponential suppression. Okay, and this is actually exactly what we expect on the grounds of this plot. As we're going higher and higher in the impact parameter, we're supposed to recover GR, and we indeed do, but up to some corrections, which are exponentially suppressed. So, OK, maybe start with Jan.
Could you say again what's this partial d?
This is just the derivative operator. The question was what this is. So this is the,
Acting on the bracket.
yeah, it's acting on the, well, on the square bracket, yes. So maybe one interesting comment here. In this limit, b squared is very compared to any other scale. So actually, this is suppressed compared to 1, and likewise for the other factor. So these gamma functions are 1, and we don't have to worry about them. Okay.
Sorry, just to make sure, I saw that you defined capital Y for large S.
Yes.
So does it mean that this formula, the formula on the left hand was also valid only for large S? Or it's also valid for small?
Yes, yes. So the question was about the validity of this formula. So just like in the QFT case, both S and B are large. It's just about the relative scaling. So we're going somewhere in the direction of T for both S and B. Both are large. OK, now we can get back to John's question, which was about the limit, the opposite limit. So when b is very small compared to this scale, and I should remind you that scale up to, maybe I should actually put absolute values, because y officially has a real and imaginary part. This scale is really this string size scale. Right, so what we're probing is whether the impact parameter is above or below the string scale. So we're essentially probing the transition between this and this regime here. OK, so in the opposite limit, what we get is that, well, we're going to get some cancellations between the GR and the stringy terms. And if you're careful about it, you would find the following expression. Plus corrections. OK? So now, in contrast with the GR answer, which if we ignore the stringy corrections, the GR answer would go like 1 over b to some power at low b. Stringy corrections actually rescue this, and they make it finite, at least above 4 dimensions. In the case of 4 dimensions, we still have the IR divergence, which survives in this case. OK, so let me summarize all this information on a plot. OK, so the plot is going to be just plotting the different phase shifts, iconal phases, as a function of b. OK, so there's going to be some transition around the, bless you, around the string scale, which, let me remind you, it goes as this. OK, so first let me plot the GR curve. The GR curve would do something like this. Well, OK, so this would be delta GR, which would go roughly as a function of b as 1 over b to d minus 4. So it would diverge for small impact parameters. Now the idea is that the stringy corrections rescue this and make it finite at low b. So the curve looks something like this. Goes like this. And then it merges to the GR expectation at large b. OK, so here I'm plotting the real part of delta string. OK. However, there's also a new effect, which is visible here. So at small b, there's still a dependence on y, and y at the real and imaginary part. So that means that the delta string has the absorptive properties. OK, and there's going to be some imaginary part that is somewhere here. And then it decays exponentially. You can read it off from here. There's an exponential decay with suppressed by this. OK, so this curve here is the imaginary part of delta string. OK, this is indeed, well, first of all, maybe are there any questions about this? Yes?
You start from this T-string expression, which is free, right?
The question was, the answer is no. So we started from this T-string expression, and you're saying naively it looks real. Indeed, naively it does look real, but we have to be careful about it actually has infinite number of resonance poles on the real axis. So really what we're supposed to do is study this amplitude infinitesimally in the upper half plane. And this is how it acquires a small imaginary part, which is related to the discontinuities across those resonances, which later on essentially gives us this phase.
And you probably have to explain what the absorption part is. Like, what's the physical?
Yeah, excellent. So the question is, what is the physical interpretation of the absorptive part? Well, the physical interpretation is that we're scattering two closed strings. and some impact parameter. And then there's this spreading effect in which at the higher and higher energy we scatter it. It essentially expands from the original LS to the final corrected version with the logarithmic correction. Okay, and at some point, if we compare that with the impact parameter, so the impact parameter is roughly this distance. So what this tells us is that this new stringy excitation, stringy modes being excited in the S channel when this scale becomes comparable with this scale or below it. Okay, so that's in fact why you can interpret this transition here as the scale at which the stringy effects start kicking in, which is related to the transverse size of the string. Yep.
So, like this limit you're studying on this larger diagram here is like when the vertical thing is you go to the iconal part, or it also goes to more like to the right.
The limit that we're exploring is roughly here or here. If that's what you're asking. Yes, exactly. And the reason why, we're not allowed to cross this line is as before, because our approximation is not valid in this regime. We would have to add loop corrections to go in this direction, just like in field theory. Yes.
But you're just taking alpha prime times as large, very large. So
Yes.
how can you see that's restricted to the iconal part?
Yes, yes. So the question is how can you see, because we only took the alpha prime S to be large, how do we see it's restricted to the iconal part? Let me just emphasize this is exactly what we've done. The same exercise that we've done in the GR case. The way that you see that something breaks down, it's studying the subleading corrections, in this case at one loop, and seeing at which order they kick in. And that gives you the shape of this line. So we should repeat the same exercise, but because of the universality of high energy scattering, we can expect that the same line holds. There was one more, yeah?
Is there some physical interpretation of the imaginary part being generated?
Yes, sorry. Yeah, sorry. So let me repeat. The question was about the imaginary part here. The interpretation of the imaginary part is that there's new dissipative modes.
How do you see that those are related?
How do you see?
That those are related, the imaginary part?
Well, the imaginary part is always related to dissipation or some radiative corrections. And this is just the interpretation of that. Yeah. Yes.
So in the QFT case, we saw that we needed to add like loops and blah 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 because we were seeing like a breakdown of some quantity somehow.
Yes.
Is there some like I don't see any breakdown that would tell me that I need to add genus correction to the 3 level?
So the question is, how do we see that this breaks down eventually, and then we need to add corrections to it? It's similar to before. We could have studied this tree level on its own. It would grow as a single power of S. This would signal that the unitarity, we need to fix it. So what we've done here implicitly is that we've exponentiated the answer. This made this pure phase, all exponential decay. And then you can ask, is there a signal of the fact that we need to further add corrections? And I guess from this perspective, the answer would be no. But we know that there are further corrections from higher genus. Yes?
Sorry, but even with this imaginary part, does unitarity not break down? If there's no extra factor such as just e to the I delta?
So the question is whether the unitarity breaks down with this imaginary part. The important fact about this thing is that it's positive. So we have exponential with I times the imaginary part of delta string. Delta string is positive, so this gives us exponential, gives us a suppression. Yeah. Yes?
From random walk, one would expect that the size of the string is proportional to the square root of this.
Yes, excellent. Yeah, that's an excellent comment. So the comment is that from a random walk picture, you would expect that we have some highly excited strings which are very windy. So the size of the string should decrease. And basically, what this computation is telling you is that there's the wave packet expansion effect, which is on top of that, and it compensates it such that the growth is still logarithmic. So this includes the windiness. It is true that all of these modes, I try to illustrate it with my cartoon here, are very excited. So they're like high energy modes, and we're actually going to come back to it. If there's time towards the end. All right, excellent. So let's move on. Yes, this one more.
Why are we allowed to exponentiate this? Because in the case of the QFT one, the loop corrections, right, they basically make powers of the tree level.
Yes.
But that's not at all obvious that here when you start doing higher genus corrections.
Yes. So the comment is it's not entirely obvious that the answer exponentiates in the same way as in quantum field theory, because we went through an intricate argument with delta functions and so on. So this is actually the reason why I skipped going through the entire argument. The answer is that there's still an exponentiation. You can see it from different points of view. There's worldsheet point of view and things like that. So the answer is that the amplitude does exponentiate, although it's more difficult to see. It's I think.
From a worldsheet point of view, it's very much not obvious, right?
Yes.
These integrals over
Yes.
moduli spaces.
I agree. Yeah. The integrals of the moduli spaces is simplified drastically in this Reggie limit, and in that limit, it's more under control. And let me also mention that on the physical grounds, we of course expect that we match on this limit in the classical when we're way above the string scale. So at least on those grounds, we can expect that some level of exponentiation happens. Okay. Okay, so let me move on to the next topic. Remember, we wanted to go from more established results to more speculations. So let me move on to the next topic, which is the generalized uncertainty principle. So as a warm up to discussing uncertainty principle, let me compute the deflection angle. Okay, recall that the deflection angle for small angles was equal to twice. Went through this little exercise at some point. Is equal to this quantity with the square root. And then the way that it's related to the iconal phase is by a derivative. Sorry, can you see this? The derivative with respect to the impact parameter of our phase shift. Iconal phase, up to some factors. Okay, so we could have gone carefully for this computation, but let me just give you the final answer. We've computed this previously in GR. Now there's the string correction to the deflection angle, and I'm going to just quote two asymptotic limits. So essentially, what you can do is you can take these two limits, very low b, very large b, hit it with the b derivative, compute this. And the answer is as follows. So in the limit as b is much larger than the string length, you get as expected, the GR expectation. Okay, so some positive numbers. Then gamma of d minus 2 over 2 plus exponentially suppressed corrections like this. Okay, that's not unexpected because of the physical picture that we have. And then on the other hand, in the small b regime, we get another answer, which we expect to be vastly different from the GR answer because of the finite size of strings. Okay, and then doing the computation, you get these various factors in here. And then the most important aspect of it is that this one has the b to the d minus 3 power, but this one scales linearly with b. Okay, so let's make another plot of the deflection angle as a function of the impact parameter. Okay, the plot is going to look like this. With B, once again, somewhere here, there's the string scale. The GR answer would just look like a power law, so it would look like this. Okay, so we know that in the large B regime, the stringy answer is going to look very similar. So it looks something like this in here. But at low impact parameters, it's linear. Okay, so the curve looks something like that. It's more difficult to see. Well, you have to be very skilled at analyzing the incomplete gamma functions to understand how this looks like. But you can do it either numerically or just connect these two curves. There's not that many things that can happen. It looks something like this. Okay, so this is the regime in which the delta string is roughly theta string is roughly theta GR, but then the aspect of string that we have not seen before is that there's some maximal angle. Let me call it theta max. Okay, theta max you can simply estimate by equating these two equations. So just like extrapolating them until they meet. And if you do this, it gives you the maximum angle of theta max of roughly g square root of s divided by the string length to the d minus 3. Okay, so how should we understand this plot? One way to interpret this plot is to ask what happens, like in a particle collider. You would scatter the particles, then you see what happens at given angles in the detector. Okay, so this would correspond to scanning different scattering angles in here. Okay, so you can be somewhere for some critical angle, the angle below the critical max. So somewhere here. And what this would tell you is that there's in principle two possible classical configurations which could contribute to classical scattering. Or another thing that you can do is study the angle, which is still small to be compatible with this quantity being small, but nevertheless above the threshold. And in this case, there's no classical saddle. Or at least from this picture, there's no real classical saddle. Instead, the path integral is still, not the path integral, the Fourier transform is still dominated by a saddle But in this case, it turns out to be complex. Okay, so let me summarize what I said. If you consider fixed angle scattering, there are two options. In this case, there are two saddles. You can actually do a more careful analysis and see which of these two dominates. And it turns out that it's always the case that the one to the right dominates. Okay, so there's the dominant saddle is always above the string scale. And then what you can do is you can also study this regime. Strictly speaking, we should be imposing that theta is still small. And in this case, we would find that there's a complex saddle which nevertheless, if you compute its absolute value of the impact parameter, it's going to be complex, in fact, almost purely imaginary. It's still above the string length. Question?
If the saddle is imaginary, does this mean that there's no like time reversal symmetry anymore?
Yes, exactly. So the question is about whether there's time reversal for a complex saddle. Certainly a complex saddle, what it's going to do is that it's going to exponentially suppress the amplitude, which is the same as saying that it's highly inelastic. So there's a lot of other kind of dispersive things going on that are not seen in this 2-to-2 exclusive scattering. Okay, so let me give you the interpretation of this result. This result basically says, in the region of validity of this computation, no matter how you choose the scattering angle, the saddle that is dominating that scattering is always above the string scale. So in a sense, you cannot probe below the string scale. This is a result, or maybe I should put it here, due to Amati, Ciaffolani, and Veneziano. From a long time ago, even before I was born. And they wanted to interpret this result as the fact that string theory somehow protects you from exploring small scales below this string scale. And then let me quote one consequence of that, which is due to Veneziano. He called it the generalized uncertainty principle. Okay, and then he was inspired by the usual uncertainty principle. But to implement the fact that somehow there should be a new scale which prevents you from probing, physics at low x, he decided to add another term, which at least by dimensional analysis, it makes sense. It's something that protects you from exploring the scales below alpha prime. Okay, as far as I know, this remains in the realm of well, there's not been that much more thorough computations to support this conjecture. Okay. Yes. 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 So the question was that this was only for fixed angle scattering. That I agree. So this whole story about not being able to probe the small scales is at fixed angle. Yeah, as far as I know, there's no analogous statement somewhere here at fixed B. That's why I said it's in the realm of speculations. Yes.
So this inelasticity that we are seeing here
Yes.
are not like string splitting, right? Because S is still smaller than B even in this limit, right?
The question is whether this is related to string splitting, and in a sense it is. So it's the sign of the fact that somewhere above here, the amplitude is suppressed. And in fact, we're going to see it's exponentially suppressed. So that means that there's really all sorts of other decay processes that we've not taken into account.
So now we are going like to the right of the plot, right? Towards like the black hole region. So in this limit, or are we still on the left?
Yes, so I'm going to come back to that, how to interpret it with regard to this plot. To actually make that connection, because here we've studied the angle, and everything there is in terms of B and S. I need to tell you what the value of the B on the saddle point is to be able to place it on this plot. But indeed, what we're going to do next is we're going to push in this direction. And there was one more question, I think. Yes?
Why is the second term not log? I thought that the application of RS as a function of S is log S.
The question is, why is this not a log? I believe, yeah, again, this is at the level of speculations. It could be all sorts of log corrections, all sorts of fun games, but I'm not going to comment on that.
Well, I mean, previously, RS as a function of S is defined as log S. So I would expect that the second term is also log delta P.
Yeah, so I mean, you could add some log corrections here. They're not going to be fixed by dimensional analysis. So in principle, you can add them. But since we're not making this concrete, I'm not going to modify this equation. Okay, so in the last 17 minutes, I'm going to try to summarize the story with how to connect this stringy regime to the black hole transition. So in order to do so, I need to first introduce this notion of the point. Okay, so the last topic of these lectures is the string black hole transition. Okay, so the idea is as follows. Let me draw an average string state that is being excited at high energy. It looks something like this. Okay, something like this. So now the idea is that the size of the string we try to estimate as this quantity here. And then what I can try to do is introduce this idea of the correspondence point. Which is to equate the radius of this excited string with the radius of the would-be black hole. The radius of the would-be black hole would be the Schwarzschild radius in here. And if I believe the story that the somehow condensate of highly excited strings create a black hole, that certainly something like that has to be the case. Okay, so I'm going to whiz through the whole argument. You can read more about it in the famous paper of Horowitz and Polchinski in 97. Let me first just equate these two scales. Once again, I'm going to work up to log corrections. So the string scale is roughly square root of alpha prime. As we've seen in the previous lectures, the Schwarzschild radius is this raised to 1 over d minus 3. And then at the beginning of this lecture, we've identified the string coupling with the gravitational coupling. And that identification told us that up to order 1 numbers, this G is G string coupling in the units of the string length, like this, and then square of s. Okay, and all of that to the 1 over d minus 3. Okay, so now what I have on the left-hand side and right-hand side is some function of s, alpha prime, and g string. So what I can do is just solve this. After a little algebra, this would tell me that s, measured in the units of alpha prime, has to be 1 over g string squared. So I'm going to call this the Horowitz-Polchinski correspondence point. So at this correspondence point, what's special about it is that many quantities in string theory and in black hole thermodynamics seem to agree. So let me give you the Horowitz-Polchinski 101, if you've not seen it before. How many people have seen this? Okay, almost. Oh, go on. Just to whiz very quickly through the arguments. Oops. You can do a little exercise, and you can compute the current temperature of strings. Which is equal to this quantity. Here. So the Avogadro temperature describes basically how many string states are being produced at higher and higher mass levels. And with the Hawking temperature, which is looked it up before. It's this number. Okay, and then of course, because we've just equated the square root of alpha prime with Rs, these two quantities up to order 1 numbers agree at the correspondence point. Okay. We can do another exercise, and we can compute I can remind you what the black hole entropy is in d dimensions. Okay, so that in d minus 2 dimensions divided by g Newton. Okay, area is simply going to scale as the Schwarzschild radius to the d minus 2 divided by g Newton. But then g Newton is expressed in terms of the g string as follows. So I can just copy the relation. Okay, and then I see that at the correspondence point, these two quantities are of order 1. So this really scales as 1 over g string, or by this relation, square root of alpha prime s. Okay, so this gives us a prediction if the story with producing black holes it was supposed to be correct, we're expecting an exponential suppression with the black hole entropy at high energy. Okay, so this gives us a prediction that if I wanted to scatter my particles in string theory, or in fact any other theory, well, in string theory, let's focus on string theory, then it's supposed to be suppressed as e to the minus s black hole. So this is really the absolute value. And this is supposed to be scaling like a square root of alpha prime s. Okay, then let me remind you, the reason why it's so suppressed is that we're really computing the exclusive amplitude. Meaning that out of all possible microstates that we could have produced as the final state, we just decided that the final states are just the original two particles, which is highly, highly unlikely with this probability. And strictly speaking, this was more or less a kind of back of the envelope estimate. So strictly speaking, we expect that there could be some additional functional dependence here on the angle or something like that. Okay, any questions? I should say that this correspondence point, so this relationship here, also gives us a better estimate. So this essentially gives you the estimate of how high the energy has to be compared to the string length and the coupling that the transition between stringy physics and the black hole physics happens. So you can actually put it on this plot, and you can estimate it as the transition happening somewhere between this and this regime to make this estimate more accurate. The question is about the f of theta. So essentially, this was the back of the envelope computation. There was a lot of twiddles and so on. So we've studied essentially the energy dependence, but the angle was nowhere here. So in principle, we think we should trust this computation up to some corrections. We've already ignored log corrections in the alpha prime. So we also kind of didn't take that into account. And strictly speaking, the angle here should be somehow not too shallow. We know that in the shallow angle regime, we're going to be in the Reggie regime, in which the amplitude is polynomially bounded, not exponentially suppressed. Any other question? Okay, so in the final couple of minutes, let me give you some evidence for this. So the idea is to connect this computation and this computation in this regime. We've already seen that this regime is dominated by a complex B, which means that the amplitude has to be, or the phase shift has to be mostly imaginary, which gives us some kind of suppression. Okay, so let me sketch the computation. I think I don't have enough time to actually go through the full computation. But we're going to resort to fixed angle scattering in this regime. Okay, in this case, the T string, once again, the way that we've done this estimate before, you write the inverse transform here with the impact parameter. You have e to the minus b dot q. And then you have e to the 2I delta string as a function of s and b. So that delta string used to be at some point on that blackboard. So let's see. Okay. So since I am running out of time, let me leave it as an exercise. It might be a nice exercise, on the flights back home. You can whip out your notebook and then locate the saddle points. Okay, so we're going to locate the complex saddle in the regime. Yes, this regime. And then let me just tell you the answer is going to be that there's going to be some critical B. This relates to one of the questions from before, which turns out to be minus I ls. Okay, so that's for the units. And then up to square root corrections. This, I suppose I called it theta string. Okay, so it's essentially this string length, but it's slightly larger by the log of the ratio, square root of log of the ratio between this and the theta max. Okay, so you can plug this in back into this estimate here. What will happen is that this term here is becoming less relevant, and the most of the suppression comes from just the Fourier part. And what you would find is that this T string at fixed angle is going to decay as this. And then after plugging in all so these are the values on the saddle. And then after plugging in all the equations, square root of S is essentially going to come from the dimensional analysis. So Q has the dimensions of square root of S. Times this log. Okay, so if you're let me remind you, this was square root of alpha prime log alpha prime S. Okay, so if you're not up for a challenge to actually derive it, I also included some references on the Google Drive in which you can find this derivation. Let me just summarize. We see that up to log corrections, the behavior is minus square root of S with alpha prime and square root of alpha prime and square root of alpha prime, square root of alpha prime and square root of S, which matches this computation, this estimate here on the correspondence point. I should say of course, you have to use that correspondence point in the last step of the computation. Oh, sorry? The question is about theta string. Oh, yes. But exactly. So from this perspective, we're scattering at the fixed angle. So indeed, if you were doing things in S and T, then theta string would have some functional dependence of S. But from this perspective, this is why I called it theta star to distinguish that. Maybe I should introduce the star here. This is really a fixed angle from this perspective. A great question. Yes?
So a couple of questions. Let's see. We already had the amplitude to begin with, so why did we have to go to the phase shift and back to the amplitude instead of just analyzing the amplitude at fixed angle?
The question is, why did we have to do back and forth going from the angle and the phase shift? The answer is that we actually didn't have the amplitude after exponentiation. So what we've done is the same exercise in the G as in QFT. You do the exponentiation in the impact parameter space, you get the exponential, and then you go back, and then you analyze the saddle by this.
Great. And then the other question is going to be at this regime, it seems like you need loop corrections, but you've included them by doing this procedure.
That's more subtle. I think the question is about loop correction, whether they're supposed to be necessary, I believe. There should be a more responsible computation in which you would include loop corrections and see that they matter or they don't matter. Maybe they correct some of these log factors. This is just very hard, so no one has done this so far. But indeed, to complete this picture, I think you should pass through some loopy corrections. So if I can have 2 more minutes. Let me just summarize the whole story once again. So what we've done in these lectures is we studied the aspects of gravitational S matrix, mostly through the lens of the exclusive amplitude of 2 to 2. Then we tried to place everything on this 2-dimensional plot, which included the energy and the impact parameter. What we've seen is that, hopefully I've convinced you, is that the regime in which the energy and the impact parameters are large is the classical regime. However, if you actually wanted to be more careful about quantifying what do we mean by the classical regime, you're supposed to tell me what is the ratio between S and B as both of them become very large. And then we've seen that depending on that ratio, we recover different types of physics from the iconal, which describes like the orbiting moon around the Earth and so on, to including finite size effects, like tidal deformations, and then gravitational waves, all the way to the black hole collapse. And then in the final lecture today, what we've also described is how to add stringy corrections. And then we've seen the smooth transition between the stringy regime to the classical universality of the leading iconal. And then in the final part, we made some speculations about how to see gravitational collapse by passing through the stringy black hole correspondence point. Okay, so with that, let me thank you for attending these lectures, and goodbye.
Well, I guess it's time for lunch. Since this was Sebastian's last lecture, let's just give him one more round of applause for the whole series. We'll see you at 2 for the final lecture.